friends, to the part 3 of this series of ray optics that we are covering. And I'm really sorry for a big delay between part 2 and part 3, but better late than be sorry. So let's get started here. Part 3 today, we are going to talk more about refractive index. So we are going to see what is refractive index, and we will also understand how that affects the ray of light that is traveling from one medium to another. And in upcoming videos, we are going to use this information to see how the lenses work, how the eyeglasses work, basically. How do they change the path of the light, and how do they see, let us see better. So upcoming videos, you'll see more application based of this. But today, let's talk about refractive index, and we will also talk about total internal reflection today. So in a nutshell, what is refractive index? It is a measure of how much the speed changes for the light when it changes the medium. So let's say light is traveling in vacuum, it enters air, what is the change in the speed? Or when it enters glass, and we have already spoken about this, light is an electromagnetic radiation. It can travel in vacuum and it can also travel in mediums, but then the speed is not same. The speed changes when it changes the medium. So refractive index is the measure of about how the speed changes when the medium changes. It also tells us how the light would bend, because when it changes the medium, obviously we know the light travels in a straight line, but when it changes medium, that the path is actually bent, and the refractive index will tell us how much it bends and in what direction. So more the refractive index, more the bending. And also understand, more the refractive index, lesser the speed of light. So let us get started with those concepts here. So this is what refractive index is, and this is the definition of it. So there is nothing I can prove here or something. It's more like a definition. So definition is, the refractive index of a medium is the ratio of the speed of light in vacuum to the speed of light in that material. So let's say I want to talk about the speed of light in glass or water. This is glass and also water. So let's talk about the refractive index of water. So the refractive index of water will be equal to the speed of light in vacuum, which is denoted by letter C. We all know that. So C is equal to 3 times 10 to the power 8 meters per second. That is the speed of light in vacuum. Now, speed of light in water. So let's say I am telling you the value. You don't have to memorize it, but let's say I tell you the value. It is 2.25 times 10 to the power 8 meters per second. So those are the calculations you would have, right? So now you can cross these out. So 8 let's do quick calculations. So that 10 to the power 8, so this becomes 300 over 225, and that gives you 25 times 1 12, and this is 9, so that is 4 over 3. So very quick calculation there gives me a value of 4 over 3. So that is the refractive index of water. What is the unit? There is no unit, because look at the units, meter per second, they cross out. So refractive index as such has no unit. It is a pure number. It's more like relative density, where you compare the density of something with the density of water. So the units cross out. Same thing here. So there is no unit at all. So let's practice more on this. But before that, here are some sample numbers to look at. You don't have to memorize any of them. The idea here is to show you different refractive indices for different materials. So for vacuum, it is obviously 1, because if you could try to calculate the speed of light in vacuum divided by the speed of light in vacuum, that gives you 1, because you're dividing the same numbers. But look at air. Air has a refractive index very close to vacuum, because speed of light in air is almost same as speed of light in vacuum. It slows down in air, but the amount of the difference in the speeds is not much. So for all practical purposes, whenever we deal with any situation involving air, we are going to take refractive index as 1. So you can see for gases, carbon dioxide, hydrogen, oxygen, all these are almost 1. Talk about liquids. Now, liquid we already calculated just now. For water, it's 1.3333, right? So for the light, when it enters a liquid, it slows down with a bigger change in the speed over there. But now look at solids. Solids, it's going to slow a lot. Look at glass, 1.5. Look at diamond. Diamond, it's very slow, and we are going to talk more about diamond at the end of the class today. And the reason that the speed is so much less in diamond is the reason why the diamond is so shiny. The glitter comes because of the fact that the speed of light in diamond is so small. So something you can pause and look at. Do not memorize any of this. This is just a general information. So speed of light is very slow in solids, slow in liquids, and fast in gases. Now let's practice. So let's calculate the refractive index of water. Let's actually, this is a mistake on my part. This is the value here is glass. So the speed I have given here is for glass. You don't have to memorize. These numbers have to be given to you. These are calculated experimentally, nothing to be memorized. So pause the video here and try to calculate the refractive index of glass. So assuming you have already tried it, let's do this together. So refractive index is equal to the speed of light in vacuum, which is denoted by letter C, divided by, and we are talking about glass. So refractive index of glass is speed of light in vacuum divided by speed of light in glass. So speed of light in vacuum is, this is one number you cannot never ever forget, because this has a lot of significance in your life. It is not just the speed of light, it has a big significance. You are traveling with the speed in space time right now. But anyways, back to the topic here. So 2 times 10 to the power 8 meters per second. And then you can see how the units cross out, how 10 to the power 8 crosses out, and the refractive index is 1.5. And what is the unit? There is no unit. Let's do another quick calculation here. And we are going to start total internal reflection after this. So calculate the speed of light in glass if the glass has refractive index of 1.5. This is the reverse of that, right? So the base, same thing. The reason I have the same question in two different ways is just to show you, just basically to put in your visual memory this formula, that's all. Because there's nothing to memorize here, this is just to just show that to you. So let's go to more stuff here. Rarer versus denser. So basically, by definition, rarer is the medium where the speed of light is more. Speed is more. And obviously the denser is the one where the speed is less. So this is more like a comparison. So let's take an example here. Let's compare air and let's compare water. So when I compare air and water, air has a speed, the speed of light is 3 times 10 to the power 8 meters per second, and this has a speed of 2.25. You don't have to memorize this, but I'm just telling you these numbers. You will be given these numbers whenever required. So basically, I know the speed of light in air is this much, water this is this much. Now let's talk about the comparison. So speed is more, that medium is called rarer medium. So you can see air is the rarer medium, and the water is the denser medium. But now let me move my picture a little here, maybe. Yeah, now let's compare water with glass. Now glass has a lesser speed. It has 2 times 10 to the power 8. So now when I'm comparing water and glass, look at how water has more speed compared to glass. So this is a rarer medium now, and this one is a denser medium. So it depends what two things you're comparing. So if I'm comparing this and this, maybe this is heavier compared to the watch, but then when I compare this with this, so this becomes light. So it's all about comparing two different things, and we are talking about rarer and denser because we'll see how the light behaves when it goes from rarer to denser medium. So again, one last time, rarer is the one where the speed is more. But then let's talk about the refractive indices. So refractive index is the speed of light in vacuum to the speed of light in a given medium. So when I'm talking about rarer medium, so if the medium is rarer, rarer has more velocity, right? Higher velocity, so it will have lesser refractive index. On the other hand, when you talk about denser medium, so denser medium will have lesser velocity, and that means it has a greater refractive index. So that's another way to look at rarer versus denser. So whichever medium has more refractive index, that is the denser medium. The other one is the rarer medium. So one with the lesser refractive index is the rarer medium. So you should pause the video, think about this, grab it in your heads, and then move forward, because I'm going a little faster, assuming that you have understood. Now, very useful law here, which is called Snell's law. When you're talking about reflection, think about reflection. In the case of reflection, what did you study? You studied, okay, there is a ray of light that is incident here, and then you draw the normal there, and then the light reflects back. And we said angle of incidence is equal to angle of reflection. That works in the case of reflections. Now, when you're talking about refractions, basically angle of incidence is not equal to angle of refraction. So this law, the analogous to this law is the Snell's law. So you should know what you're studying as a big picture first of all. So in reflection, I equals to R. The equivalent of that here is the Snell's law. I will not equal to R. It will be something else, but it is calculated using the Snell's law. So let's talk about it. Let's say there's a ray of light. This is the flashlight that is throwing the light on water here. Some of the light is going to be reflected back. See how the light is reflected there. And some of the light will go into the medium. So when the light goes into the medium, so that's refraction of light, right? So refraction of light is the bending of light when it goes from one medium to another. It was air and it is going into water. So when it travels from air to water, look at how it was supposed to go in this direction. It has bent now. So bending of light when it changes the medium is called refraction, and so this is the refracted ray. So again, some light out of this incident ray is going to be reflected, some light will be refracted. So reflected rays, see how it is following the laws of reflection. Whatever was the angle there is the angle of reflection. So that part is covered. But now you can see this ray is not following that law. Theta 1 is not equal to theta 2. So how are they related? How do I know that? So Snell's law, very easy law. Many books confuse you by saying sin I over sin R is mu this and that. Do not worry about that. The best way to understand Snell's law is this, and I'll come back to this slide. So the best way to understand Snell's law is mu times sine of theta is equal to a constant. And I'm going to prove this when we study wave optics, by the way. So when we study wave optics, we will see why this is true. It's very simple. It's a two-line derivation, but let's wait until we cover the wave optics. What does this mean? This means, let's say there is a ray of light that is traveling and then it encounters another medium here. So let's say this was glass or whatever. Now it is going to bend. So first of all, we measure the angles from the normal. So I'm going to draw a normal. So let's say this was medium 1 with refractive index of mu1 or n1 basically. I think I've confused you by writing mu there because we have been using n for refractive index. So let's continue that. So n times of sine theta is a constant because mu is another symbol used for refractive index. Let's stick to one symbol for now. So let's say this is a medium 1 with refractive index of n1 and this is another medium with n2. Now let's say this angle here is theta 1 and then light enters the other medium and theta 2. So theta 2 may be more than this, less than this, I do not know for now. But what the Snell's law tells you is refractive index times of sine theta is a constant. So what you would do here is you will say n1 sine of theta 1 is equal to n2 sine of theta 2. Any of these angles may be incidence angle, another one may be refraction angle, doesn't matter. So you can just plug in theta 1, theta 2. If this is the case here, this is the incidence angle. So instead of this, you can plug in sine I, and this is R, so you can plug in sine R. So but remember the Snell's law, and this is going to help you a lot if you remember in this way. N times of sine theta is a constant. Many books will tell you sine I over sine R is mu I R, what 1 2. It's very confusing, and that doesn't always work because now look at this. Let's say this is medium 1 with refractive index 1, then there is another medium with refractive index 2, then there is another medium refractive index 3, then there's another medium refractive index 4. So you can have n number of media. Now let's say there's a ray of light that is traveling and then it does all those zigzag whatever. Right. So now let's say you just want to find this angle. This angle is what you want to find. Now, obviously what you would do is this is theta 4, let's say, and this is theta 1. and let's say this was theta 2, right? All these angles theta 2, and then here is theta 3. But then what is the law? Law says n times sine theta is constant. So you can say n1 times sine theta 1 is equal to n2 times sine theta 2 times n3 sine theta 3 is equal to, so you can keep doing that. So ultimately, if you just want to calculate this, you can bypass the medium in between there. So you can just say n1 sine theta 1 is equal to n2 sine theta 2 is equal to n3 sine theta 3 and so forth. So you don't have to consider those medium in between. You can directly write n4 sine theta 4. So that is Snell's law. Snell's law is n times of sine theta is a constant. So let's move further and see what that means. How let's practice on that. So uh, let's say this is medium 1. Let's say this is medium 1 n1, and this is n2, or but better yet, let's say this is n rarer, n denser. So the point is it's going from a rarer medium to a denser medium, like air to water, air to glass, something like that. So how does the light behave? So let's draw this. And before even I draw, I know Snell's law is nr sine of theta r. Theta r as in the angle in the rarer medium is equal to n2 sine theta d. D as in denser medium. Right. Now remember, what is a rarer medium? Rarer medium is where speed is more, but refractive index is less. So this number is less, and this number is more when you compare those two numbers. Yeah, that's by definition. Rarer medium has less refractive index, denser medium has more refractive index. I wrote 2 there, but that's ND, let's say. Now, if you're multiplying two numbers on left side, multiplying two numbers on right side, they have to be equal. Then obviously this is pure mathematics, no physics. This number has to be more now, and this number has to be less. Now sine theta increases with theta. So can I not say that theta r has to be more than theta d? Right, pure logic there. There's no like calculations there. But if nr is less, then theta r, sine theta r is more. If sine theta r is more, theta r is more. What that means is this. Let's say there was a ray of light, and this was theta in the rarer medium. Theta in denser medium has to be less. So that means it is going to bend towards the normal now. And that's another thing you're supposed to not memorize here. You're supposed to understand why that happens. Because see, the light was going in this direction, but it has bent towards the normal. So when it goes from rarer to denser, it is going to bend towards the normal. So let's practice one more like that. So let's say in this case, the light is going from denser to rarer. So this is mu d and this is mu r. So again, going by the same logic, mu d, I don't know why I keep switching between mu and n here, because I love that mu symbol somehow. So, but then I started with n here, so I'm going to stick to that. So nd sine theta d should be equal to nr sine theta r. And the same logic applies here. Because this number is more, this number has to be less compared to, right? So then theta d has to be less than, and that's kind of like law now, right? Theta d always has to be less than theta r. So let's say this was my normal, and there's a ray of light that is traveling here. This is theta d, but theta r has to be more. So light was going in this direction, theta r has to be more. So it will bend there, as in it will bend away from the normal. So when light goes from denser to rarer, it bends away from the normal. And this is what we will be also use when we study the critical angle. So anything that is not clear, please take a pause and rewind the video. So bends away or not towards, let's see. So when it goes from rarer to denser, it bends towards. Don't memorize this. This is something you can do it in half a second maybe. Denser to rarer, it is going to bend away from normal. And this is towards or away from normal, not from the surface. We always, by convention, we always take all these angles, directions from the normal, the 90 degrees line there. And that is a convention for reflection as well as refraction. So moving forward, uh, let's see, total internal reflection, a very beautiful phenomenon. It's very pretty, and a rainbow is formed because of this. The mirage, if you have seen the mirage in hot summers, it's summer weather right now. So you're driving on a hot summer afternoon, and then you on the road you think there's a patch of water, but then as you go closer to that, there is no water. It was just an illusion. And that happens in deserts. So the poor deer, he or she thinks there is some water there, starts running towards that, and then eventually it turns out there's nothing, and the poor deer keeps running, because as the deer comes closer to that, the water patch has moved forward. This is all total internal reflection. In upcoming videos, maybe I'll make tiny videos talking about that, but today I'm going to talk more about fiber optics and rainbows as applications of this. So but let's understand what is total internal reflection. Very basic idea there. There's no big kind of, so let's say there is a light that is going from denser to rarer medium. And that's the key here. Let's say it's going from denser to the rarer medium here. And we all know the light goes away from the normal, right? So we have already seen that. So let's say there's a normal here, and there's a ray of light that's traveling in this direction. Now it is going to bend away from normal, obvious, right? So nd times of sine theta d is equal to nr times sine theta r. So basically this is the thing, nd sine theta d is equal to nr sine theta r. Now let me write that properly, because that's going to be used here. Nd sine of theta d is equal to nr times of sine theta r, right? Now these values tell us that it's going to bend away, but now these values are fixed, right? For two given media, they are fixed. Let's say I start increasing this theta d. I start making this as more. So then in order to keep that constant, this also will increase. So when this increases, this number also increases. So my point is, as I increase the angle of incidence here, the angle of refraction also increases. So when I throw the light at this angle, the light bends more, right? So more and more and more. But it will actually happen that for a certain angle here, the light actually has bent so much that it is going at 90 degrees angle from the normal now. It is just at the border of those two surfaces. So for a particular angle of incidence, this angle is going to be 90. Because now this is very interesting, because now if I increase any little more, if I increase the angle thoda sa bhi zyada, a little more than that, so look at what will happen. Let me use a black color here. So let's say a blue color here, that's fine. So let's say I make the angle a little more, the angle of refraction will be more than 90, but that means it has come back to the same medium. So again, a kind of revision here. So what I'm saying is the angle of incidence is here theta d, but then angle of refraction is more. So the light has bent away from the normal. But as I start making this far and far away, this also starts going far and far away for a particular angle of incidence. For some angle of incidence that we will calculate, the angle of refraction will be 90. But if I throw the light a little more than that angle of incidence, for which this is 90, it will bend more. So then it will come back into the same medium. It is behaving like a mirror now. So let's calculate that part. So let's say I want to calculate how much is that angle for which angle of refraction is 90. So here is the quick calculation here. So for a certain angle, of incidence, this angle of incidence, the angle of refraction will be 90. Now, let me use a straight line tool there. This, right? So for a particular angle of incidence, the angle of refraction is 90 degrees. And this angle of incidence is called the critical angle, because that's a critical angle, that's a borderline. If the angle of incidence is less than this, the refraction will happen. But if angle of incidence is more than that, then this will happen. Look at how the light was going from water to air. This was water and this was air. the light never goes into the air, it travels back into the water. It's more like a reflection here, but this is not a mirror, these are two transparent media. So this will happen. So how do you calculate the angle, critical angle? Simple, Snell's law. So Snell's law would be n of d times sine of critical angle is equal to n of r times sine of 90, but sine of 90 is 1. So you can plug that 1. So sine critical angle is equal to nr over nd. Now, obviously, if R is sometimes air, like you can see in the case of this air and water, so this will be critical angle for water air combination would be, so you would plug in 1 here and you will plug in 4 by 3 here and do the calculation and you get the values now. So this is how you calculate the critical angle. Once you know the critical angle, you know if the incidence angle is more than critical angle, the light is going to come back and total internal reflection will happen. So let's move on and study more on this. The diamond, remember, if you remember those values there, don't have to memorize, but remember diamond had one of the most refractive indices. It has a very slow speed actually, and that is the reason it has such a big amount of let's do a quick calculation there. uh, Let me go to another slide. So basically, you don't have to memorize. The refractive index for diamond is 2.4, roughly in that range. Now, if you do 2.4 is equal to speed of light in vacuum divided by speed of light in diamond basically. So velocity in diamond is 3 over 2.4 times 10 to the power 8 meters per second, right? So that is 6 over 5, that is 1.2 times 10 to the power 8. See how slow the light is in diamond. Diamond has a very less speed of light, and that is why the refractive index is so much more. But that helps because see, remember now if I try to find the critical angle, so let's take the value here and try to find the critical angle. Let's say the light is going from diamond, this is diamond and this is air, and then you do, I'm doing from the very basics. I'm not using any memorized formula here. I'm just relying on the Snell's law. That's one thing you memorize. So this is the behavior. It has to be 90 degrees here. So mu of d. So let's start the plugging in the value. So mu of d is 2.4 times sine of critical angle is equal to mu of air. Mu of air is 1 times sine of 90 is also 1. So sine of critical angle is equal to 1 over 2.4. So let me see if I have, yeah, I have a calculator handy here, luckily. Yeah. So let's do that. So 1 divided by 2.4 gives me 0.4166. I don't know if you can see that, right? So that's 0.4166. Now, critical angle is going to be arc sine of that. So let me try to do that. Arc sine of 0.4166 gives me only 24 degrees, my friend. 24 degrees, that's all. So any light that is more than 24 degrees incident is going to come back. So let's see how that helps now. So light is going into the diamond here, and see, this is 24, tiny angle there. So all the light that is at this angle, all that light is going to be reflected back. So if you're observing the diamond from here, so most of the light that is traveling into the diamond is coming back, and that's why you see all this glitter here. And obviously it's not just the diamond, it's the craftsmanship of those artists, the craftsmen who actually carve it in that way. So that's why you have to craft the diamond, not just the raw diamond. They cut it in such a way that the light that goes in, most of it comes out. So that's one application of total internal reflection. Let's move forward. So like bending of light. Let's say you want to bend light. One option is take mirrors, but mirrors are not 100% reflection. They're going to absorb the light. But this is total. The word itself is total. So if it is total internal reflection, all the light is going to come back. Now, if you do the same kind of calculations for water and air, use a calculator if you have to. So not water and air, sorry, glass and air combination, the critical angle is going to come out something like 42 degrees, roughly in that range. But now if you have a 90 degrees prism here, the light is falling. So see, the light goes in, the angle of incidence is 0. So angle of refraction will be 0. Light will go straight into that prism. But here the angle of incidence is 45. It is going to come back. And when it is total internal reflection, no Snell's law there. Now it is more like angle of incidence will be equal to angle of reflection. So now when this is 45, this is 45, and the light has been bent by 90 degrees without any absorption. Same thing, you can bend the light 180 degrees. So there is one internal reflection happening here, sorry, and then another here. So light has been bent 100% by 120 degrees. Had this been a mirror, mirror is not 100% because it absorbs light. We use this in binoculars, so we have to bend the light. See how we have to bend. We could have used mirrors, but mirrors are not going to be reflecting 100% of it. So note the word total internal reflection. So let's see how fiber optics works. So most of you might be already knowing fiber optics is the data carrying thing. That's the thing that carries the high speed data. So how does that work? Let's actually see the basic concept there. So let's say there is a house here, and very vague kind of analogy or example, but this will help you understand. So let's say there is a house here, and I have to my house maybe to your house. I have to send the data. So how do I send data? I can use data cables, right? I can lay the data cables there, but data cables will carry the data at the speed of data, which is not fast. We know the fastest thing that can ever travel is the light. So how about I have some device, and we already have those devices. We can convert data. Let's say D stands for data, that converts it into light. So now light will travel with the speed of light. On the other side, I have the other device that converts light back into the data. So the problem solved, right? Convert data into light and then transmit it with a high velocity, and then at the point of usage, convert the light back into data. There is one big problem. Light travels in a straight line. So how do you make that travel? One option is, which is not practical actually, is perfectly straight tunnel between those two houses. Let's say 500 kilometers house. So first of all, it has to be perfectly straight. Secondly, it is point to point. How do I send the data to this house now? So that's not a practical kind of thingy. So you cannot use the tunnel to send the signal in a straight line. So how do we do that? Another trial would be, okay, how about maybe this is bent, but then how about I make this out of mirror? If this is mirror, what will happen is light enters here, it is reflected here, it is reflected. All these are mirrors, let's say, and this is a practical solution. But think about, mirrors are not 100% reflective. Let's say very high quality mirror, let's say it absorbs 0.1%, let's say 0.1% is what it absorbs, which is a very high quality, very costly mirror. But then think about it, every time the light is reflected back, it has this much of energy. But then a millions of those, and then you have to the power of 1 million. Think about the exponential decay that is happening here. You have virtually no signal at the other end because you're not getting 100%, and there are millions of reflections. But the solution here is very simple: fiber optics. So let's say the inside material, this material is a denser medium, and this medium is a rarer medium. Outside medium is rarer medium. Now the light is traveling here. Look at the angle here. So much of angle. If these are thin, see, if these are thick, there is a possibility that the angle here will not be critical angle. But then let's say it's very thin. Whatever light enters in, see how big the angle is. It's going to be more than critical angle, and that's why these fiber optics you can see here, they are very thin. So light enters the fiber optics here. Let me erase all this. Oh, this is rarer. I'll leave it here. So light enters here, it's trying to go from denser to rarer, it hits more than critical angle, the light reflects back. And then it reflects back, it reflects back. And this is how the fiber optics works. And because we have to make it thin, we make a bunch, we make a big bunch of these thin ones. And this is how fiber optics works. Another application of total internal reflection, which is more beautiful now, it is the rainbow. But before that, let's see what is how the light behaves in a prism, and we'll go into the rainbow now after this. So let's say there is a prism here. Now the prism is made of glass. So let's say this is all air outside and this is glass. Now obviously air is a rarer medium and glass is a denser medium. So rarer to denser, it has to bend towards the normal. So first of all, I draw this normal here. The angle of refraction is less. It has bent towards the normal. You can see that. Now on the other side, you do the same thing, the light has to bend away from the normal. So see how the light has bent towards the normal and away from the normal, and because of the geometry of the prism here, the light was actually going in this path and it is going in another path. So light has been bent now. Now this angle, the angle between the original path and the new path, this angle is called the angle of deviation. So see, I'm trying to give you an overview of everything here so that you don't have to memorize things. You can understand the concepts. You can go back to your books. Now, when you study these things will look like very easy for you. I'm not saying whatever I'm teaching in this 45 minutes is going to be enough, but it's going to give you a big head start here. You know everything overall, and also you know the behind the scenes things which are not covered in the books. Now you have to read the book today, because by tomorrow it might be gone from the head. You might have to revise it. So read the book today and everything will be so clear. Now let's see what more. Let's before I cover another slide, let's cover this. So when you talk about waves, you have already studied this in your junior grades. Velocity of a wave is equal to frequency multiplied by the wavelengths, right? Now frequency and wavelength, so let's not go into those details. Let's talk about the blue light. Blue light is a tiny wavelength and high frequency, and the red light is huge wavelength with a very less frequency. You got to know those things because these things will be used in wave optics also. Now talking about the speed, when we talk about the speed, the way speed works is, I'll cover that here. So when you're talking of vacuum, all the rays of light, all the frequencies, 3 times 10 to the power 8 meter per second for all colors, not just all colors, even infrared, X-rays, gamma rays, all of them have this speed. But when you talk of a medium, and here is the key to the rainbow formation, the velocity of violet is slowest. Right, let's write Vibgyor here, so that way it's easier. So Vibgyor, that's the rainbow colors. Now red travels the fastest in a given medium, and the violet travels the slowest in a given medium. Right, the slowest and the fastest. But what does that mean? The fastest has less refractive index. So let's write it down. Mu is least and mu is more. Mu or n, I'm really sorry. So refractive index is most. But what that further means, so look at this. Red is fastest, so refractive index is least. So bending is least. Bend least. And violet will bend more. So see how this is like when they change the medium, not all colors will be bending with the same kind of angle there. So see how that helps here. So there is an incident ray here which is white light. This is Vibgyor. So this is Vibgyor. Now when look at this, the light is bent towards the normal, but you can see red light is bending, but violet is bending so much. And then again on the other end, the light is bending away from the normal, but look at the red. Red is not bending that much compared to violet. So all the Vibgyor, that is one white light, has been separated into 7 colors now. And this is how you see these beautiful rainbow colors. And let's see how the rainbow actually is formed. So let's take a drop of water, and many things are happening right here. So there's sunlight which is white in color, and that sunlight, if you look at this normal here, the light which is red in color has bent, but violet has bent more, and all the other colors are in between. Obviously, we are not showing them for clarity. Now, when the light hits here, the light hits at an angle more than the critical angle. So there is a total internal reflection happening here. Now the light comes out here. Now you can see the light will bend again, but the amount of bending in violet is more than red. Other colors are in between. So there's indigo, blue, green, and all that, right? So there are 7 colors here. Now let's see how that helps, because now there are so many water droplets. So there was a rain, and there are so many tiny little water droplets out there. So the water drop here, just look at the top water drop here. It has separated into red and violet and all that. But the light that this girl is receiving from this is red. So this girl says this water drop is red in color. That's what she says. Now the girl says this right here, this one. This one is sending the rays of light in different directions for the different colors, but the girl receives violet from this drop. So the girl thinks this drop is violet in color, because whatever comes to your eyes is the color of that object. So you can see how beautifully the rainbow will be formed, because the drops at the bottom will look like violet, then indigo, blue, and all that. So this is how the rainbow is formed. So today I have covered refraction. I'm going to cover lenses, but with the lenses I'm going to cover a lot more, because I have to cover the lens maker's formula and then also cover different combinations of lenses. So lens itself is going to be a multi-part series that is going to start in next 2 or 3 days. So next time, as I promised, I'm going to do lenses. When we do lenses, I'm expecting that you will study a little, think about a prism when you're thinking of lenses. So remember how the ray of light which is traveling here bends, right? So think about a convex lens as two prisms there. So light is bending there, light is bending there, and it might be focused here. We are going to cover that very soon. So I promise within next 4 or 5 days, I'm going to bring up another video for lenses. In the meantime, please rewind this video and see whatever you have not understood, and you can put in the comment section. Please do write in the comment section if this is useful, because that's how I will know if this has helped somebody and I get motivated to make more videos. So put in the comment section below how useful this video was. So until then, let's go through this really nice code. You miss 100% of the shots you do not take. So very nice. If you do not try something, let's say you're playing a basketball, you don't try a shot, that you've already missed it. Because if you try something, there is a big chance that you might fail, maybe. But there is also some chance maybe that you will succeed. But if you don't even try, then there is zero chance. Maybe when you tried, there was a negligible amount of chance, but now when you don't even try, it is a zero chance. So you have missed 100% of the shots. So even if something is very difficult and the chances of success is very small, at least try that. So thank you, then I'll see you soon. Bye bye.